Right, so welcome everyone to this new video where we discuss mathematics and physics on the board. In this video, we are going to discuss a very simple kind of formula, which is that of the group velocity of a wave. And in fact, that's usually the group velocity, yes, of a wave, but more readily so, the group velocity associated to a way a wave is actually moving. That's actually a bit more accurate. And so basically that's it. The way we are going to see that is by using a very simple example and try to see what kind of unfolds from that example. Right, okay, so as I said, what we are going to do is look at a very simple example. Now, the concept of group velocity contains the word group, and as you know, a group is a collection of things, okay? And in particular, in that case, a group can be considered as a collection of waves. And so that's what we are going to look at. Now, the smallest group you can form of waves is basically a group of two waves. And so here I'm considering a signal which is actually made of a group of two waves, and these waves have frequency omega 1 and omega 2 respectively, and corresponding wave vectors k1 and k2. I'm going to go back to this word that I've used here, corresponding, because this is very important to go to or to get to the actual final formula. Now, often again, the final formula that you're going to see is very known. Usually it's kind of sometimes just given as is, or sometimes it requires a sort of extremum stuff, but then it's difficult to understand what's going on, what the physics behind that stuff. And hopefully this is what we are going to see here. So the first thing to notice is that we've got different, so let's say this thing is a prototypical example of the simplest, if you will, of wave packets. Okay, so that's a wave packet. And because I'm adding up two waves, two signals. Now, one of the things that one caveat I want to put here is that on purpose, I've put the same amplitude for both waves, but that's not necessary to actually work out what's going on. But it's easier to see it, obviously, the way then we are going to see things. And you're going to see why this is important. So the first thing we are going to do is try to express K1 and K2 in terms of some mean and the mean, let's say, frequency and wave vectors and mean differences, if you will. So it's not necessarily a mean difference, but it's a sort of mean difference. So we introduce basically K as being equal to K1 plus K2 over 2, and then delta K as being, for example, K1 minus K2 over 2. Now, the reason why I do that is because it looks as if there was no, relation between K1 and K2 here, and I want to relate them to something they have in common, and what they have in common is basically this kind of mean, okay, so that's the arithmetic mean, and this kind of weighted difference, okay? So the thing is, from this, I can actually get that K1 is equal to K plus delta K, and likewise K2 is going to be equal to K minus delta K, right? So if you add K and delta K, you see that you're going to get K1 over 2 plus K1 over 2, so that's K1, and then K2 over 2 minus K2 over 2, so that's 0. You do get K1 indeed, and likewise for K2, okay? So what I do then is that I can substitute these expressions into these ones. And this is going to look kind of the same, by the way, for omega. So K is that, and then same for omega. So we've got omega is equal to omega 1 plus omega 2 over 2, and delta omega is omega 1 minus omega 2 over 2. And so we are going to get omega 1 is equal to omega plus delta omega, and omega 2 is omega minus delta omega. Okay? So then what I do is that I substitute that in there. So we've got f of xt is equal to a, and then cosine of, and then omega 1 we've said is equal to omega plus delta omega. So that's t minus k plus delta k, and then that's x, and then plus a cosine, and then omega minus delta omega t minus k minus delta k x. Okay, so that's the expression we have. What I'm going to do now is actually group these terms in terms of omega minus k, so omega t minus k x, omega t minus kx, and then separate it from all the terms that depend on delta omega and delta k. Okay, so this same expression is going to be equal to, so that's a, and then we've got cosine. So now let's look. So we've got here omega t minus kx, and then we've got plus delta omega t minus delta k x, and then we have the same thing here, plus a cosine, and then we have omega t minus kx minus delta omega t minus delta k x. All right? So what I do then after that I use the expression or the double angle formula that cosine of a plus b is equal to cosine a cosine b minus sine a sine b. Okay, so that's going to be complicated because I want to apply that to every one of them. Okay, so this is going to lead me to f of xt is equal to, so let's see, so this is a, and then I've got cosine, and then omega t minus kx, so that's, let's say, just put parentheses, so and then cosine delta omega t minus delta k x, and then here I can put as well, so I've got minus sine k, sorry, that's not k, that's omega, omega t minus kx sine delta omega t minus delta kx. And I can do the same here, so plus a, and then I've got cosine omega t minus kx cosine delta omega t minus delta kx, and then plus sine omega t minus kx, and then sine delta omega t minus delta kx. And as you can see, the two terms on the right hand side cancel out. So one is simply minus the other, and so these terms kind of disappear. And so what I'm left with is basically this particular expression. I've got 2a and then cosine of omega t minus kx cosine delta omega t minus delta kx. So I've got a product of cosines, and the thing is that they don't go at the same frequency. So this one is omega, and it's going to be the average kind of frequency of omega itself. So of omega 1 and omega 2, so that's the arithmetic average. So essentially it's going to be a relatively large term, which is commensurate, let's say, with the typical value of omega. However, delta omega is actually the difference in frequency. So if we assume traditionally like frequencies to be like positive numbers, then if I take the difference between two numbers, then this is going to be different. And notice that in the case of omega, the closer omega 2 is to omega 1, the closer it's going to be to some omega which is the same, which is basically omega 1 or omega 2. However, here, the closer omega 1 is to omega 2, the smaller delta omega is going to be, okay? And so basically the same goes for delta k. And so what that means is that you've got here something that oscillates. It's a sort of wave, but that then oscillates with very high frequency omega. And then here something that is multiplied by it, but then that is at low frequency, okay? And so this is basically this particular kind of waveform. This second part, which is slowly oscillating, is called the envelope. The envelope. I don't know if there are two P's of the wave packet. Okay, so this is slowly varying, while this part is kind of the signal, this is kind of fast varying part of the wave. So you've got a fast varying part of the wave which is modulated by an envelope part of the wave, which has this kind of slow frequencies in space and time. Okay, now the thing is that how does that look like? Well, if we have that delta omega, and respectively for delta k as well, is much less than omega itself, then what that means is that essentially you're going to have plenty of periods within a very small interval of delta x or delta t. Okay, you're going to have plenty of these periods. And what that means essentially is that you're going to reach the maximum value, so the number 1 here, for basically all possible values of that. Okay, and so essentially that's when it becomes a real envelope. Okay, it's because for every t, almost for every t, you're going to have a corresponding maximum value for cosine of omega t. So it's going to draw this maximal value. So it's going to draw like a border, which is essentially that function. So one way to represent this, maybe I can put, so let's say this is the amplitude of the wave. And here you go, let's say I'm at fixed time. And then I'm plotting that with respect to x, and that's kind of f. So what you're going to look at, and I'm not sure I'm going to do that well, but essentially you're going to look at this cosine value. Now you need to be careful that this thing is going to be maximum at both, or extremum at +1 and -1, right? So cosine is bound between 1 and -1. So this thing is going to be oscillating between -1 and +1, essentially sampling the upper value and the opposite image value with respect to the x-axis. So first of all, we are going to draw this envelope kind of like this. Okay, and I need to draw the actual mirror image relative to the x-axis because again, both of them are being sampled over a single period of this fast varying thing. So we are going to have something like this. And then, of course, this would continue and so on. And then what I'm going to do is then try to draw the fast varying part. So you've got inside of it an actual signal, which is very fast varying. It's just I can't do it kind of very well. Okay, so that's basically your wave packet. And so you've got like very fast varying wave, which is essentially enveloped and kind of transported by this global looking envelope. And what we call the group velocity is essentially what is the velocity of that envelope. Okay, so the group velocity means basically the phase velocity of the envelope. Again, I put 2p, maybe it's because that comes from my mother tongue, it doesn't matter, um, it's just spelling. And so this particular phase velocity is actually delta omega over delta k, okay? But, and that's crucial, that's going to be equal to omega 2 yeah, okay. So let's say actually, so that's omega 1 minus omega 2 divided by k1 minus k2. And then that's the crucial part where I talked about corresponding k, okay? Because we need to remember that these guys are waves. And so what that means is that they follow they are solutions to a wave equation, which allow them to actually propagate. And what does that mean is that wave equations come with what we call a dispersion relation, especially if they are nonlinear or if they have some specific boundary conditions for certain direction and not others, they are going to have specific so-called dispersion relations. And essentially this means that there is a relationship. Okay, so it's a sort of equation of state in thermodynamics, but in this case, this is actually for waves, and that's a relationship between omega and k. So you can't basically change independently the value of k and that of omega. You actually they are connected to each other. So if I actually write that, for example, k1 is equal to k2 plus some delta k, then I'm going to get something like this. I'm going to get that this is omega of k plus delta k minus omega of k. So let's say k1, k2, sorry, and then divided by delta k. And then when we look at the limit of that quantity, when delta k tends to 0, so if I look at the limit when delta k tends to 0 of this delta omega over delta k, I actually end up here with the definition, basically the definition of the derivative. And so this is going to be equal to d omega of k dk. Okay? So that's how it works. And that's basically a typical example where we get, so this thing is actually called the group velocity, so often denoted Vg or Cg, depending on who you talk to. And this is basically different from the phase velocity of that wave, which would be, some omega over k, for example. Okay, so that's kind of the bottom line, and usually that's kind of what you would be given essentially like right away without any particular understanding about where this is coming from. You're told there is this so-called phase velocity, which is that, and then there is this other so-called group velocity, that is this other formula. And often you're told, well, the group velocity is the one that is really carrying information. The phase velocity is not, but often that's where it stops. And so actually it comes from something like this. Now, of course, these things are a bit more complicated if the coefficients are changed. However, you're going to get this kind of signal nonetheless. It's just that it's going to be a bit more messy because you're not going to have an exact compensation here, and you're not going to get these kind of things. However, essentially, the basics of the physics going on is basically characterized by that particular graph here. So I hope that it helped a bit understanding what this group velocity is about. Often this is some kind of mysterious subject, or at least concept that you need to learn by heart. And if you've got any questions or comments on this, by all means, do let me know in the comment section. And otherwise, see you in the next video.